So yesterday, we looked at feed-forward networks, how to train those networks, the very basic fundamental neural network. We then looked at how we teach networks to interpret and process sequences of data. And today we'll look at how neural networks can interpret images. First, interpret images, and then imagine, hallucinate images with generative networks. And what are images? There's nothing special about images. They're just numbers. It's a collection of pixels. For a grayscale image, that pixel is a single number. For RGB images, that pixel is 3 numbers. You can get fancy. You can add some depth. That's 4 numbers. But it's just numbers. And what do we do with neural networks? We just feed it numbers and produce an output. Let's focus today in the first lecture on the problem of classification, of looking at an image of a cat. You will be seeing a lot of cats today. It is because, well, cats are fascinating creatures, but they're a good illustrative case study of why computer vision is very difficult, and we'll see exactly why. And classification is the task of taking in a collection of numbers that represent an image and saying, is this a cat? Is this a dog? The fundamental question we'll answer at the end of this lecture. It's a philosophically challenging one. So let's take a step back. Okay, when you saw that image of a cat, you're like, that's a cat. I know that's a cat. It's pretty easy. But it's actually one of the most difficult things for a computer to figure out. What is in this collection, a spatial collection of pixels? Why does it seem easy for us? Because we're cheating as human beings. The neural network inside our brain, inside us, the real neural network, has had a lot of data. Data is king for this neural network and for the artificial neural network. We've had 540 million years of data for visual perception to learn how to see. And the stuff that seems so complicated to us, like chess, playing chess, having conversation, like intellectual conversation with your buddy about who should have won the election, that seems so difficult. Because we've only recently, 3 orders of magnitude less data, only 100,000 years of abstract thought through evolution. Here's a visualization of a simulation of the human brain to give you a sort of why neural networks on a philosophical level are so captivating to us as human beings, and an inspiration, a crude one, for the structure of a neural network. Here is, on the bottom left, is an activation, retinal activation of obviously, I'm not a neuroscience guy, so I apologize if I'm using the incorrect terms. But on the bottom left is the activations of retinal activations when your eye is taking in a certain signal. And then the rotating there is a 3D model of the different neurons in the brain, especially the visual cortex that's being activated when those inputs are provided to the visual stimuli. The visual impulses are being fed into the brain. That's what you're seeing there is 8 million cortical neurons getting excited because they just got some signal. And there's 2 billion synapses connecting those cortical neurons. Those are the connections that we talked about for a neural network. That's the inspiration for a neural network, or an artificial neural network that processes images, a convolutional neural network. The same process in the visual cortex in the human brain you can think of crudely is the same process that happens in a neural network when it's given images. The earlier layers form, starting from raw pixels, form primitive representations of what's in the image, edges, primitive shapes, corners, and then higher and higher order of representation for the entire image, of what's the actual semantic content of the image. But don't let your brain fool you. Computer vision is hard. You have to be able to classify an object as being the same thing, no matter the orientation, the viewpoint variation. Light. The reason we see anything is because light is reflecting from it and providing texture information about it. So the position of the light changes everything in terms of the numbers that are represented in the collection of pixels. There is deformation. The objects, especially cats, can be deformed in arbitrary ways. There's occlusions. You know, the occlusion is one of the most difficult problems in computer vision. It seems absurd, but if I put my hands over my face, it's still a face. But for computer vision and face recognition, it becomes a lot more difficult to detect that it's a face. It's a fascinating fact that we take for granted, that we just need to see a little bit of that cat at the top right corner, and we know it's a cat. And for the process of supervised learning, of image classification, when we have images and labels, for this very fundamental process repeated over and over, we need a lot of data. We need data where a human being has stepped in and annotated the ground truth, the truth about the contents of those images. Here are some famous data sets. MNIST, a data set of handwritten digits. ImageNet, we'll focus in on ImageNet today as a case study. It's a collection of 1,000 categories, 14 million images, all from the internet. CFAR 10, CFAR 100, simplifying the problem down to 10 or 100 categories with little tiny images. And then Places, here from MIT, is a data set of natural scenes. So let's take a small step back and figure out, before we get to play with neural networks, how would you do it in a different way? In order to classify an image, you have a new image coming in, and you have an image of a cat, and you have a bunch of images of cats and a bunch of images of dogs. And you have to try to figure out, is this image that just came in of a cat or of a dog? How would you do that? Well, you have to compare. One way is to just look through every single image you have. You have 10 cats, 10 dogs, and say, well, what am I looking at here? And you have to then have an operation that, given two images, gives you the distance between those images. How similar are they? So one way is just to take a collection of pixels, grayscale pixels shown there, 4 by 4, the test image and the training image, and just take the absolute difference, pixel by pixel, pixel-wise, and then sum it all together. And so between those two images of 4 by 4, the difference is all adds up to 456. And so if we try to classify in CFAR, CFAR is a data set with 10 categories: airplane, cat, dog, of course, frog, horse, ship, and truck. And if we try to classify using this simple classifier and saying, I'm going to put this new image that came in into the category that is closest. I'm going to define the image that is closest to the one that just came in and put it in the same category. So if we were just randomly guessing, just guessing a category 1 out of 10, our accuracy would be 10%. Now, if we use this new clever algorithm we've designed that actually looks at the entire data set and compares to every single image and finds the one that's closest, we'll get 30%, in the 30s. This is the process. Bottom left there. You have a new guy coming in, green. And you have a bunch of blue and red, blue squares and red triangles, and you're trying to figure out the new green guy, does he belong to the blue squares or the red triangles? And nearest neighbor, we can compare to the closest. Well, the closest neighbor is a green, is a red triangle. So let's put it in that category. But what if we look at the 3 closest neighbors? Well, 3 closest neighbors and then take the majority is still red triangles. But if we look at 5 nearest neighbors, then blue is the majority. This is the fundamental, simple but powerful algorithm for machine learning as k nearest neighbors. And then in the exact same process, we can optimize the hyperparameters. We optimize the learning rate, the various hyperparameters that control the neural network the same way. There's one hyperparameter here, that's k. And we can optimize it, shown on the x-axis in the bottom right. X-axis is that k parameter. Y-axis is the accuracy you get. You can play with it. It turns out that the optimal for the case of CFAR 10 for nearest neighbors is 7 nearest neighbors. You have to look at the 7 closest neighbors. And the accuracy you get is still in the 30s. Now, to motivate the power of convolutional neural networks is human being performance on CFAR 10, this data set of 10 categories, is 94%. It's fascinating, by the way, how you get that. If there's questions, I can elaborate. Convolutional neural networks is 95%, currently state of the art. And what is a convolutional neural network? The building block is the same as we talked about yesterday with feed-forward networks, with recurrent neural networks. There is inputs, some weights, sum them up, add a bias, and a nonlinear activation function. Forward pass, backward pass. Backward pass over the gradients that provide you an inkling of how to change the weights in this network to optimize the loss function. Same process. So with a feed-forward network, how would we classify an image? For this MNIST data set of handwritten digits, we could take 28 by 28 pixels. We could just take all of those pixels and shove them in. That's 784 neurons. Just take every single pixel, grayscale, and give that grayscale 0 to 255 value, 784 of them. And as an output, produce 10 different outputs. Softmax, probability that this is 0, a 1, a 2, and so on. There's no convolution there. Feed forward. The problem is when the images get large, that input gets huge. So convolutional neural networks have a volume, a 3D volume. They see the input. They see the spatial information in the input as valuable for processing that input. An image has spatial information. Pixels that are close to each other are close for a reason. And the extra addition that a convolutional neural network provides is a convolutional layer. I'll explain exactly what a convolution is. We'll take it step by step. I think that's a fundamental but a very important thing to understand. But high level, you just add, when there's images, you add an extra convolutional layer and a ReLU, a nonlinear, a sigmoid, a tanh, a nonlinear activation layer function, some pooling, and repeat that process over and over and over, and then at the end, get to the fully connected layers. The insight, in the same way that we talked about yesterday for recurrent neural networks, where parameters, in order to deal with arbitrary sequences, words that are in the beginning of a sentence have the same meaning as at the end of a sentence, you have sharing of weights in order to take advantage of the spatial independence of the position of those words in a sentence. In the same way, there is spatial independence for features in an image. So as opposed to looking at the entire image as a whole, connecting every neuron to every other neuron in a fully connected way, we can use the same process as our human vision takes, is narrow the receptive field. Only connect neurons in the input field, a small collection of neurons in the input field to a neuron on the output, and slide that focused receptive field across the image. What is this sliding process? What is convolution? Let's take it step by step. We'll make these slides available. I think you should step through it carefully to understand how beautifully simple convolutional neural networks are. On the left is an RGB image, 7 by 7 by 3. A 7 by 7 pixel RGB image with 3 RGB depth 3. So you have depth 1 is the first gray box, grid. Depth 2 is second grid, and so on. 3. Just want to make it clear. On the right in green is the output of this fancy convolution. And the output is depth 2, is 3 by 3. In the middle are the filters, are the weights that we're trying to learn in a neural network. These weights are the ones that transform from the left, the input, to the right, the output. But they don't transform the entire input of 7 by 7. They slide the window, and the weights are shared. So what you'll see in the middle, as we slide this window across, is the weights remain the same. And what you see on the right, highlighted in the green box in the grid, is the output of the computation shown on the left. So let's start in the very beginning. There is a 3 by 3 receptive field. This convolution is size 3 by 3. And we apply a filter, the first filter, to each one of the depths in the image. And then sum those together to produce the output, -3. This process is then repeated. It's a dot product, a multiplication, and a sum to produce the output. There's a padding of 1, so we pad the input such that we can always squeeze that 3 by 3 convolution in there, and the jumping, the stride, is a step 2. So the convolutions jump every 2 grid sizes. Now, what can we achieve with this convolution process? For example, there's a funky-looking creature, not sure what it is, but that's the input image. And the output, so if we take a convolution filter like this up at top, it's an identity filter, where there's a 1 in the middle, zeros everywhere. If we slide that filter across, the output is going to be the same image. Now, edge detection. We can make those filters detect certain types of edges. And then the input, if we slide those filters across the input, the output will be activations. The parts of the image that contain edges will get excited, will have high values. And parts of the image that don't have any edges will remain low. Looking at it another way, sliding the visualization there of a edge detector, a specific kind of edge detector. This is a convolution filter. You slide it across the image, and the output will be another image that tells you, that gives you activations. Here's the parts of the image that contain this exact type of edge. And that's what convolutional neural networks are, is a composition of these filters. At the very beginning, on the bottom, layer 1, are very primitive filters, edges. Then you start composing those features together for higher and higher order representation of features to form corners, in this case of a face, parts of a face, nose, eyes, eyebrows, and then entire faces in the very top layer. And then there is another operation. So we've talked about the fully connected operation yesterday. We talked about convolution operation just now. And then there's also pooling, which is more and more going out of favor. It's an operation that reduces the size of the input and the output, and there is, most importantly, no learnable weights on this operation. It uses the fact that there is spatial consistency in the image to save some computational power to reduce the size of the network, to try to optimize, to minimize, to reduce the number of parameters. So we'll look at a bunch of applications. Why are convolutional neural networks so cool? Well, they're cool for two reasons. One, first of all, images are cool. But two, the fundamental architecture of a convolutional neural network remains the same in all of the applications we'll talk about. And what is that architecture? So you have an input set of images or an input image, video or image or some kind of visual information. There's convolutional layers with nonlinear activations. There is possibly some pooling, and that's it. You just repeat that, convolution, nonlinear activation, and pooling over and over. It gets a little fancy, as we'll talk about. There's some nice little variations, but fundamentally, that's what it is. And at the very end is some fully connected layers. Or, now that's what we talked about, some fully connected layers to tell you the difference between a bird, a sunset, a dog, a cat, and the image. But there's other applications. First, you can, for ImageNet, because these are 1,000 categories, you can chop off, through a process of transfer learning, chop off that last several layers and put in your own specialized set of layers that can be retrained, keeping the first part of the network fixed. Retrained for a specific application, of face recognition, of bird species recognition, and so on. That's image classification in different domains. You can, and I'll go over that in a little bit more detail later, is for image captioning, the input's still an image, there's still convolution, there's still max pooling. But the output of those features extracted on the left side of this diagram are fed into a neural network to generate language, to generate captioning. As opposed to just classifying what's in the image, we can do object localization, localizing where exactly in the image that cat is. So the output is not just the classification, but also the bounding box of where in the image it is. Again, chop off the right part, just have a slightly different output. It gives you the coordinates of the bounding box. You can, as opposed to classifying, you can also do fully convolutional networks or generative networks with deconvolutional layers where the output is a segmentation. This is a narrow specific application of generative networks where the output is a pixel by pixel segmentation of the image. Pixel by pixel segmentation of the image such that you're not just localizing with a bounding box, but localizing every single pixel. So let's look at the thing that, if you talk about computer vision, if you talk about deep learning, this is one of the applications that, like New York Times, the media, if you want to write a blog and you haven't, I heard this machine learning thing, ImageNet is one of the things that comes up. Now, ImageNet is, first, this was brought up to me recently, that it's unclear what ImageNet is to a lot of people, actually. So let me be clear about what ImageNet is and what all the different terminology around ImageNet is. First, ImageNet itself is a data set. It's just a data set. There's 14 million images in it currently with 21,000 categories. And let's zoom in and look at the category of fruit. There are almost 200,000 images of fruit. Let's zoom in on Granny Smith apples. There's 1,200 of those images of those apples. That's what's in here. And those are links to images, not the raw images themselves. So what is ImageNet? ImageNet is a data set. There's also competition, which is what people often think of as ImageNet. It's not. It's the ImageNet Challenge, the ILSVRC. And there's a bunch of networks which demonstrated on this process of image classification, on this data set of ImageNet, in the competition of ILSVRC, that deep learning has something special. It started in 2012 with AlexNet and continued on to today. The performance, and there's a lot of fascinating details here. They're left in the slides, and you can always talk to me afterwards. These networks, some of them just made things bigger and deeper, and some of them fundamentally changed the architecture involved. AlexNet was the first deep neural network, 8 layers, 61 million parameters, a big leap forward in this challenge to 15.4% error. The next year, deeper and bigger, reduced to 11.2%. A slight change, but again, deeper and bigger with VGGNet, VGG16 and VGG19 with 16 layers, 138 million parameters. Then GoogleNet got clever, did a lot of interesting optimizations with inception modules. Fascinating stuff there. Would love to talk to it about it forever. Reduced it down to 5 million parameters and a 6.7% accuracy on ImageNet. And the state of the art today is ResNet, residual neural networks, that for the first time ever, the tricky thing, and I joke, deeper is better, bigger with neural networks is better, but it wasn't necessarily true until ResNet. These residual networks, the more layers you add, the higher the accuracy. For the first time ever, this very particular kind of architecture allows for backpropagation to not significantly suffer from the effects of a super deep network. So ResNet in 2015, the one that successfully won, had 152 layers. And kind of boring this year, CU Image won with an ensemble of 6 models, meaning no significant breakthroughs, but aggregating several models together. And there's a bunch of details here on each network. You can look through in the slides. So the applications are all reliant on the same kind of architecture. The first part is convolution, convolutional layers, nonlinearity, pooling. And the output is X, something. In the case of segmentation, that output is more convolution, where the input is an image and the output is a heat map that gets excited when it sees that, in this case, a cat. Pixel-wise segmentation. There's object detection, where you can use that information of a pixel-wise segmentation to give you a few candidates, as opposed to sliding a convolutional neural network across an image, a very expensive and computationally challenging task. You can give it a very small number of proposals, 10, 100, on the order of hundreds of proposals of where a cow is in this image. And so you only need to then classify a few of those candidates. Is this a cow or not? Makes object detection much more efficient, very powerful. So applications getting fancier now. Bringing RNNs in is image captioning, image caption generation. A lot of breakthroughs there. So you take as an input as an image, produce a heat map, and then localizing those individual components, so detect all the different words going on in the image, and then use RNNs to stitch those words together into a coherent sentence, and then rank those sentences the most likely of being associated with that particular image. Same thing with question answering. You can provide an image and ask a question. What is the color of the cat? Same process. The input is a set of images. The CNNs, in that case, extract features that can then be operated by a recurrent neural network, an LSTM, to generate, to process the question and generate the answer. Same thing for videos, quite obviously. Videos are just a sequence of images. And so you can use recurrent neural networks with the convolutional neural networks extracting the features, and the recurrent neural networks making sense of the temporal dynamics from image to image as represented by those features. You can use, again, a combination, they're best friends really, a combination of RNNs and convolutional neural networks to steer. The RNN steers and the CNN recognizes. You can steer the convolutional neural networks across an image to recognize, in this case, street numbers. Oh, didn't know audio was on. You can you don't have to just put images. As long as it's a collection of spatially relevant information, you can just put a spectrogram. On the bottom there is a representation of audio signal coming from the road. You can put that in. You can use that for voice too. Recognize the gender of a voice signal. Put it inside of convolutional neural networks. The constraint, as opposed to a recurrent neural network, is that the chunks that you put into a convolutional neural network have to be fixed size. If something's not fixed size, you have to, our best friend, RNNs, has to step in. And driving scene segmentation. Again, we're starting to get into this domain where the convolutional neural networks aren't just classifying cats versus dogs. They're also helping intelligent systems operate in this world. This is a visualization of segmenting the driving scene, roads, street signs, and so on. Or this is the source of excitement for the artificial intelligence community in general, is as opposed to doing all the fancy segmentation work, detecting where the road is, detecting where different things are, whatever the application is, sort of breaking that application down into different pieces and solving one piece at a time. You know what? We're going to do it the same way that humans do it. When you first learned to drive, if you ever learned to drive, you were tossed into a car and then you just learn and there's somebody yelling in your ear maybe, but all you're getting is visual perception and all you get to do is steer. So the nice thing we have is in this application of driving, end-to-end driving, is we have a lot of data. So we can just take in an image and produce a steering command back, end-to-end. That's a convolutional neural networks, as simple as it gets. Now, let me sort of end with a dose of reality a little bit. So as these exciting constructs, the convolutional neural networks that now do better than human beings at recognizing images, contents of images, as we try to use those algorithms for robotics, for the operation of intelligent systems, we have to now come to the reality of some open problems, of robustness. These algorithms can break down easily. This is a seminal paper. The deep neural networks are easily fooled. On the top is shown a set of images that by, I believe, VDGNet can be recognized as, there's noise, but what it confidently, above 99.6% confidence, says that there's a robin, a cheetah, an armadillo, and a lesser panda in the top, in that noise. And same in the bottom. It confidently says there's a king penguin, a starfish, a baseball, and an electric guitar. Obviously, there's not any of those objects. In the same process, you could take a correct image where the classification is correct, and you can add a little bit of noise, just a little bit of noise. And you can confuse the networks to predict that there's an ostrich. As an input, you can take a school bus, add a little noise, and that's definitely an ostrich. So this is for, it's okay to miss that every once in a while for an ImageNet. It's hard, right? Ostrich, they all kind of look the same. But when you have to control an intelligent system, a robot operating in an industrial application, or a car that's driving 65 miles an hour and down a highway and controlling the human life, that becomes a lot more important. And here's the most important problem that boils back down to the fact that computer vision is hard. The occlusions, the pose variations, the lighting variations, and occlusions, I think, is one of the best examples of, I apologize for the pun, of category recognition. This is still a cat. This is still a cat. This, with some category confusion, is still a cat. And I know that most of you were fooled and thought that this was a monkey eating a banana. But in fact, this is still a cat. Okay, thanks, guys. The slides will be up. Hey, great job. Thanks, man. Yep. Always finish with cats, I think, is the... So still...